Wowzers, I really can't believe it, but we're halfway through Calc 1 here. Our topic today is Riemann sums, and basically, to summarize a Riemann sum, it approximates the value of a definite integral. So you'll notice we've got a lot of words here that we haven't seen anything remotely related to. So basically, to summarize Calc 1, there are two foundational ideas in Calc 1, and we can check one off our list officially today. So the first thing is a derivative. We've spent the last few months talking about. The derivative is something that measures instantaneous slope. To summarize that in a nutshell, instantaneous slope. Okay. Now we're going to graduate to our second foundational idea, and that's an integral. And basically, an integral is something that measures area bounded by a curve in the x-axis. Well, I really wish my handwriting was a little neater on this rascal, but I think we can fight our way through it here, hopefully. It just measures the area bounded by a curve and the x-axis. Now, specifically here, when I say integral, I'm referring to something that we're going to talk a little bit later about a definite integral versus an indefinite integral. But that's really what I want you to take away here today, is that a derivative measures slope and an integral measures area, and that, ladies and gentlemen, is everything you need to know about Calc 1. Okay, so we hinted at the fact that there are two types of integrals, one being a definite integral and the other being an indefinite integral. Now, I'll start off with an indefinite. An indefinite integral is basically what we call an antiderivative. In other words, we're just doing the opposite action, as far as our analytic algebraic skills. So an indefinite integral is one that, this is our integration symbol here, and maybe we're integrating x squared with respect to x, and his antiderivative would be 1/3 x cubed plus c. Now, if you're scratching your head wondering how in the world I got that, don't worry about that. We haven't covered or taught that yet, of course. But basically what I want you to notice there is there's no bounds on the integral. There's no bounds. Okay? That's all you need to know today, is that an indefinite integral is an integral that has no bounds. And specifically, there's no little number here or at the top. Now, a definite integral is the type that we're going to try to approximate today. Okay? This is one that does have bounds. So maybe, maybe we're integrating from 0 to 2. X squared dx. Now we're going to find out that our answer to that is 8/3. Okay, so what you noticed here is that definite integral does have bounds. I had a lower bound of 0 and an upper bound of 2, and notice the difference in answers. My answer to an indefinite integral was a function of x, whereas my answer here to a definite integral was a numerical answer, not a function. It's just a number. And what that number does, as this picture down here indicates, is that number indicates the area bounded underneath the curve and the x-axis, and you'll notice the shaded region started at x equals 0 and extended until x equaled 2. And the area bounded by that curve is 2.6 repeating, which is equivalent to our 8/3. Just to totally summarize everything that I tried to spit out, a definite integral can be summarized by this beautiful picture right here, and I want this picture to be firmly ingrained in our mind as we go through this next piece. We've got a lower bound of a, so you notice we have a vertical line at x equals a, and the upper bound is b, so we've got a vertical line at x equals b, and those are some boundaries. We're always bounded by the x-axis, and then whatever function we're integrating, which in this case is f of x, is clearly denoted by the blue curve here. And so the integral is going to measure, and I'm going to add a word here, the exact area. Alright, now tonight we're not going to worry about the exact area, we're only going to worry about approximating the area. We're going to get as close as we possibly can to the real number, but it's going to be an approximation. So here it is, ladies and gentlemen, a Riemann sum. And a Riemann sum, by definition, is a numerical approximation for a definite integral. So that n shouldn't be there. For a definite integral. Numerical approximation for a definite integral. Alright, now there are 4 types, and we're going to cover 3 out of the 4 tonight, and then in tomorrow night's video we'll cover the 4th one. Not that it's that much harder, but just to break it up a little bit. The first one is called a right Riemann sum. The second one is called a left Riemann sum. You'll notice how creative these names are. The third one's called a midpoint Riemann sum. And the fourth one that we'll save for tomorrow night is called a trapezoidal approximation, or a trapezoidal Riemann sum. And so these were pretty fun rascals, and I think we're ready to dive in. So here's our very first Riemann sum, and we're going to really rely on having some great sketches and some really accurate drawings to help us visualize and appreciate what it is that we're actually finding tonight. So we're trying to attempt to find the numerical answer to this definite integral. Now exactly what is this definite integral measuring? Alright, so we're trying to picture this parabola that starts up here at 25 and intercepts the x-axis at 5 right there. But the integral is only going from 0 to 4, so we're not going all the way to 5. So we'll say 4 is right there. And what we're trying to do is we're trying to find all the area from x equals 0 until x equals 4. So we're basically picturing this region right here. And again, it's not a nice geometric shape. It was, it's straight on 3 edges, straight boundary, straight boundary, straight boundary. But then it's this curved edge that causes us trouble and makes it a little more challenging to find the exact area. So tonight, all we're going to do is we're going to focus on finding the approximate area. So I'm going to redo my drawing here really quick. I got a y-intercept at 25, and like we said, we intercept the x-axis at 5. 1, 2, 3, 4, and 5. Okay, now here's what they want. They want 2 subintervals. That's all we're going to do, and we're going to make them equal tonight. And we're using a left Riemann sum. So here's how this goes. My first interval is going to be from 0 to 2. And my second interval will be from 2 to 4. But what I want to do is, if this rascal right here is the base of my rectangle, I want to extend that rectangle upwards until the left edge, or the left vertex, hits the curve. And then I'm just going to extend straight across, and then I'm going to run straight down, and that's what we'll call our first left-handed rectangle. Now if we wanted to try to express the area of that rectangle right there, we know that he's got a base of, well, just remember, of course, area of a rectangle is length times width. So the area of this rascal, it's got, we've got a base of 2 units, and the height, it looks like it's going to be 25 units. Now, how did I get 25? The left edge here hit the curve, so I'm going to say f of 0, which turns out to be 25. So 2 times 25, and that rascal has got an area of 50. All right, now we needed 2 rectangles. Now, the second rectangle is going to go from 2 to 4. I'm going to extend the left edge up until it hits the curve, right about there. I'm going to shoot straight across, and then I'm going to shoot straight down, and that's my second right-handed rectangle. Now again, we've got a base of 2 units, and this time the height is going to be f of 2, because I started at x equals 2 and I shot straight up until we hit the curve. And let's see, f of 2 is going to be 21. And so I've got an area of 42, and therefore I'm going to claim that my total combined area with those 2 rectangles is 92. And I did want to ask myself whether we had an under or an overestimation here. And what we're going to do is we're going to say, because the rectangles did accumulate some area that fell above the curve, these 2 rectangles overestimated the actual value of the integral. But we'll say that that definite integral is approximately 92. We virtually have almost the same problem here. The only difference is they wanted me to use 4 subintervals, and we're going to see if that can positively or negatively impact my answer. In other words, is my approximation going to get more accurate or less accurate as I increase the number of rectangles? And so let's go 1, 2, 3, and 4. And let's see, the first rectangle is going to only go from 0 to 1. I'm going to extend it skyward until we hit the curve. Straight across, straight down. What you'll notice is we do have less wasted space up here, so it feels like my approximation is going to be a little bit more accurate. And the area of that first rectangle is going to be, it's got a base of 1 and a height of f of 0. And f of 0 turns out to be 25, so I've got a grand total of 25. Alright, now the second rectangle is going to have a base that starts at 1 and ends at 2. I'm going to extend straight up until we hit the curve. Alright, and the area of that blue guy still has a base of 1, and the height is going to be represented by that point on the curve right there, and that's going to be f of 1, which in this case is 24, so the accumulated area is 24. Again, just a little bit of an over approximation there, not too bad. Not too bad. Alright, my third rectangle is going to extend from 2 to 3. I'm going to shoot up until 2 hits the curve, so f of 2 is that point right there. straight across, straight down. All right, and so I've got a base of 1 unit and a height of f of 2, which is 20. And I've got one more rectangle to go. Let's grab yellow here. So I've got a base that goes from 3 to 4, shoot straight up till 3 hits the curve, straight across, straight down. Again, a little bit of an over approximation, and I'm not sure if you can see this yellow too well, so I'm going to switch it right away here as soon as I finish this. But we've got a base of 1 and a height of f of 3, and f of 3 is going to be about 16, so I got 16 there. So if I added all of these 4 rectangles up together, I'm going to end up with, let's see, 16, carry the 1, I'm doing old school math, 86. Alright, so that's a smaller number than we had with 2 approximations, and it is a better approximation. It's still an overestimate because of these little spaces up here in the top corners, but it's a better approximation. It's more accurate. So basically, one of the big things we want to take away here tonight is our accuracy improves. Oh my goodness. My goodness, my spelling couldn't be worse, could it? Our accuracy improves as the number of rectangles increases. And that'll be true in all cases. Alright, again, we've got the same definite integral. We're going to integrate from 0 to 4 of the function 25 minus x squared, but this time we're going to use 4 subintervals, and they're going to be right Riemann sums. So we're going to just practice drawing a right Riemann sum and finding the height of each rectangle. So I've got the same curve again, 1, 2, 3, 4. And let's see, the first rectangle is still going to have a base from 0 to 1, but this time what we're going to do is we're going to extend the right edge of the curve straight up and then straight across. And you'll notice it just fits underneath the curve. It's a little bit of an underestimate because of some open space there at the top. I'm going to say the area has a base of, the rectangle has a base of 1 and a height of f of 1. Notice I'm not using f of 0 for the height because it's the right edge at x equals 1 that hit the curve, and so I've got an area of 24. My second rectangle goes from 1 to 2. Again, we want to lift the right edge up, extend the right edge up until we hit the curve. Once you hit that curve, go straight across and straight down. And we still have a base of 1 but a height of f of 2, and that gives me 21. Alright, moving right along, the right rectangle starts at 2 and ends at 3. I'm going to lift it up until 3 hits the curve. There's my height right there, straight across, straight down. Alright, area, base of 1 unit, height of f of 3. That's going to give me an area of 16. And then last but not least, I got to pick a little better color this time. Let's see. Ooh, yeah, some pink. Alright. 3 to 4, lift it up until 4 hits the curve, straight across, straight down. And let's see, we got a base of 1 and a height of f of 4, which is going to give me an area of 9. And our grand total area, if we add all those rascals up together, let's see, 30, 54, and 64. How about maybe 70? 70. Did I do that? Yeah, that looks about right. Okay. Is it an over or underestimate? It's definitely an under approximation just because we've got a lot of daylight here underneath the curve, so we've underestimated the actual area. Again, if I wanted a more accurate answer, I would increase the number of rectangles. I'd go from maybe 4 subintervals to 8 to 100 to 1,000. And you could just imagine, what if I tried to fit 1 million rectangles within the interval 0 to 4 and just how accurate that approximation would be. So I know this whole Riemann sum thing is kind of a wild idea, so appreciate you hanging in there and fighting the good fight tonight. We're going to do one more. I'm going to introduce you to a midpoint Riemann sum, and I did change my mind. I originally had 4 subintervals here, but I thought it'd be better off if we just started by doing 2. So we've got the same old curve, and we're going to go 1, 2, 3, 4. Now we're going to do 2 rectangles. So the first rectangle is going to start at 0 and end at 2. But this time, instead of lifting up, the left edge, I'm not going to lift up the right edge. What I'm going to do is I'm going to find the midpoint of my base. And I'm going to extend that straight up until the midpoint hits the curve. That's what I want to do. So the moment that, I'm going to do a dotted line here. The moment that x equals 1 hits the curve, that's going to be the top lid of my rectangle. And you'll notice some of it's underneath the curve, some of it's above the curve. So what's the area of that rectangle? Well, I've got a base of 2 units, but what's my height? Now remember, my height's represented by that point right there, and that's going to be f of 1. So I've got an area for that particular rectangle, let's see, 2 times 24, 48. All right. Now, the second rectangle is going to start at 2, extend to 4, I should say. And what we're going to do is we're going to extend this rectangle until x equals 3 hits the curve, because 3 is the midpoint of my base. And let's see, I'm going to draw a little dotted line to help me visualize it right there. Boom, there's f of 3. Extend the top of my rectangle straight down, straight down. Again, we've got a little bit of an under, a little bit of an over. It almost kind of cancels each other out. My area, I got a base of 2 and a height of f of 3. Let's see, f of 3 again was 16. 2 times 16 is 32. I've got a combined total area of 80 square units. And I'm going to tell you what, that is really crazy accurate to the real answer, just because we did have some under, but we also had some overestimation, and those kind of cancel each other out. Now, it's impossible for me to tell whether my 80 is actually an over or an under, so we're not going to worry about that. But we just know it's really, really close. Now let's go back to my original intended question on that particular one. If I did want to do 4 subintervals, it does get a little bit trickier using a midpoint Riemann sum. Now here's what's going to happen. My first rectangle goes from 0 to 1, and what I'm going to do is I'm going to extend it up until the 0.5 hits the curve. So f of 0.5 is going to be my first height. And let's see, let's say f of 0.5 is right there. I'm going to go straight across, slightly over, slightly under. And so the blue rectangle has a base of 1 and a height of f of 0.5. And let's see, my next rectangle, my height's going to be, see, the midpoint is going to be 1.5. So f of 1.5 is going to be my height, f of 3 halves or 1.5, whichever you prefer. The third rectangle starts at 2, ends at 3, so my midpoint's 5 halves or 2.5. I'm going to find his height, and that's going to be my top of the rectangle. So you notice if you're doing a midpoint right, typically the top of the rectangle is going to kind of underestimate a little bit and overestimate a little bit. And f of 5 halves or 2.5, whatever you prefer. And let's go for some pink again maybe. And my fourth rectangle starting at 3, ending at 4, so I'm going to find the midpoint's height. Boom, right there. And let's see, still got a base of 1 unit and a height of f of 7 halves or 3.5. And of course we could use our calculator to evaluate all of these respective heights and come up with a final area. Alright, I just want to get a little more practice in here tonight before we call it a night about deciding how wide my bases are going to be and just making the correct drawings and determining my heights. Probably determining the heights is the most important part of tonight. But anyway, we have this definite integral. And we're trying to measure the exact area underneath the curve starting at x equals -2 until x equals 4 here. But they only want me to use 3 subintervals. So what I'm thinking is -2 to 0 is my first interval. And then 0 to 2 would be my second. And then 2 to 4 would be my third interval. So starting at -2, and I'm using a right Riemann sum this time. So let's see, my base goes from -2 to 0. I'm going to extend upward until my right edge hits, and I'm going to go straight across and down. So you see that that rectangle grossly underestimates the actual area, but I'll tell you what, we're accomplishing what they want me to accomplish, I guess. So I got a base of 2 and a height of 1, that's it. Alright, the next interval starts at 0 and extends to 2. And so we're going to extend upward until the 2 hits the curve. My goodness gracious, look at this. Now this rectangle is grossly overestimating the actual area. So you see how they kind of tend to average out and balance each other out. But we've got a base of 2 units and a height of 5 units. That would be f of 2, which in this case is 5. And let's see, that's a 10. And then my last interval goes from 2 to 4. Now, if I use the right edge is already on the curve, so I have 0 height for this last rectangle, as weird as that sounds. Area of 0 for a grand total area of 12 square units. Alright, exact same function. We're going to use a left Riemann sum this time. So still going to use the same intervals. I'm going to go from -2 to 0, then 0 to 2, and then 2 to 4. So if I've got a base of -2 to 0, I'm going to extend upwards until my left edge hits. I'm going to shoot straight across and straight down. And again, we are largely overestimating. We've got a base of 2 and a height of 5 units for an area of 10. My next rectangle is, let's see, I'm going to go up until the left edge hits right there. Boom, straight across. And let's see, we've got a base of 2 and a height of 1 is all. So there we go. And the third one, starting at +2. If I lift it all the way up until 2 hits, look at this rascal. Very large rectangle. And let's see, base of 2 and a height of 5 again. So we've got an area of 10. Grand total this time is 22. And you notice how much that answer differed from our right Riemann sum and how drastically different they can be at times. perhaps our most challenging one to visualize when you're first introduced to a midpoint Riemann sum. If I use a base of -2 to 0, the midpoint of that base is right here at -1, and so I want the height at -1, and I'm just going to go straight across right there. So let's see, there's my desired height, straight across. And I've now created my midpoint rectangle there, and let's see, I've got a base of 2 units and a height of 2 units for an area of 4. Again, you know, not a perfect estimation, but again, it's works out pretty good in the long run. I'm going to find the height at x equals 1 because that's my midpoint, so I want to go right there, straight across, straight down. So this picture is really good at just helping us being able to visualize the rectangles and get them drawn accurately. Got a height of 3 units for an area of 6. And last but not least, I want the height at 3, which is going to put me right here. Pretty darn good estimation, I would say, on this one. Base of 2 and a height of 4 for an area of 8. And grand total for area of 18 square units. So all in all, a pretty darn good night tonight. I want you to walk away here knowing a few key vocabulary terms. If my integral does not have any bounds on it, then what it is it's called an indefinite integral, and the answer is simply a function. And we're going to talk a lot about indefinite integrals in the next few days as soon as we wrap up Riemann sums. But tonight's focus was on introducing you to a definite integral, and the idea that it measures the exact area underneath the curve bounded between the curve and the x-axis and the vertical lines at x equals a and x equals b. And the answer to that is actually a numerical answer. It's just a simple number that measures area, and we approximated those definite integrals with a series of Riemann sums in the form of a left, a right, and a midpoint Riemann sum. Tomorrow night we're going to tackle a trapezoidal approximation. We're going to introduce you to some word problems and give you a glimpse of just how prevalent these actually are on the AP exam. No matter how easy you think they are, the College Board does value this idea and this concept, and we're going to take advantage of that and really nail these questions. So good luck tomorrow, and we'll see you.